So I'm going to talk a little bit about an algorithm called Floyd-Warshall, after two of the inventors of this algorithm back in the early 60s. And it uses an idea called dynamic programming, which sounds so much cooler than it actually is. So that being said, it actually is a very cool idea. I have a professor friend who believes that I am predisposed to see all problems as dynamic programming problems because it's an algorithm design technique that I have been able to use successfully on a bunch of occasions. But it really is just an algorithm design technique. It's not particularly dynamic, and it doesn't really change the way you think about programming. It just has to do with optimizing using tables. All right, so let me start off by explaining this algorithm in terms of a simple but possibly strange idea. So first, just for simplicity, let's imagine all the nodes in our graph are numbered from 0 to n-1. And lots of graphs, that is exactly how they're structured. But for example, for our Marvel data set, we'd have to have all our characters be assigned numbers from 0 to n-1. But it's an easy thing to do. Let's imagine that's already been done. What we're going to imagine now is that someone has given us this matrix, square matrix, D sub k. And the entries of this matrix, it's just a big table, like a spreadsheet, and it's filled in with values as follows. So the ij element, the ith row, jth column, is filled in with a number, and that number is the length of the shortest path from I to j, hopping only on nodes numbered less than k. So I don't know about you, but I used to play a game like this when I was younger. If I was in a building where the tiles were different colors, I'd sometimes declare, let's say the blue tiles are alligators, so I'm not going to step on any of the blue tiles. And I'd try to, walk stepping only on the tiles that I was allowed to use. So that the analog of this in the graph is, imagine we've got our graph and we're trying to get a path from I to j, and some of the nodes are colored pink. Those are the OK nodes because they are numbered less than k, and some of the nodes, maybe even including j itself, are numbered higher than k, and we're not allowed to step on those. So we're trying to get from I to j. We're allowed to step on j, obviously, but only the intermediate nodes that are pink. So we only consider making paths along pink nodes, and there's only one in this case. But there's some pink nodes that we don't use, and there may be multiple different pink paths, but we want to know the distance of the shortest path using only the pink nodes, only the ones that are numbered less than k. So let's imagine someone very helpfully has done this for us and filled in the matrix with all those values. There's big theta of n squared values that have to get filled in. But someone's done that for us. That's all great. Our mission, should we choose to accept it, is to fill in dk plus 1. So this will be a new matrix, just like the old matrix. But now, when you're going on a path from I to j, you're allowed to use node k. You don't have to use it, but you're allowed. So that's all we have to do right now is try to figure out, if someone gives us dk, how do we figure out dk plus 1?